Okay, so I think we can get started. So for those who are still working on the course evaluations, you can maybe use the time after the class to work on it. So again, I really appreciate any of your comments. Okay. So this class, we're going to finish the last part of the air pollution. It is going to be about the meteorology and air pollutant transport. So I want to say that the pollution emission or the pollution control is a very important item in air quality control, right? So that's why people came up with all of those fancy devices. For example, the cyclones, the ESP, the filters to remove those pollutants. But what's also equally important is the transport of these pollutants. So just imagine if we're planning to build a new nuclear power plant, let's say nearby the coast, right? Well, we know that the wind is always blowing the pollutants into the ocean or over the ocean. Then no one would complain about it because it's not affecting anyone, right? But if people are living downwind of that nuclear power plant, then there will be a lot of complaints because people worry about whether these air pollutants might get inhaled into the respiratory system, right? So I would say that the meteorology and the transport of these air pollutants are also very important. So this class, we're going to cover these topics. So again, if we do a quick recap of last class, so last class, it's a recorded lecture. I think quite many contents were packed into that recording. So here, I'll just quickly go over them. So last class, we talked about the particulate matter, which has several properties. For example, it can scatter light, which is giving us different colors of the atmosphere, right? And then we also mentioned that particulate matter can have a climate effect, not only because they can scatter basically solar radiation back in the universe, but also because they can form clouds and then further lead to a cooling effect. Because if our Earth is fully covered by clouds, then all the radiation will just get reflected and the temperature of the Earth is going to cool down. So we also mentioned that there's a health effect of the particulate matter when they are inhaled into the human respiratory system. And we mentioned that the size distribution is very important. So basically, what size distribution shows is the particle concentration as a function of particle size, right? So let's say if it has a size of hundreds of nanometers, let's say 200 nanometer, then based on the deposition pattern of these particles, we know that these particles are very difficult to deposit into the respiratory system. Basically, we inhale them in and exhale them out, right? That's how our lung works. But if the particles have different sizes, then they may have very high deposition efficiency. So that's why we need to control these particulate matter, given that it is a criteria air pollutant. So people design the cyclones, the ESP, which stands for electrostatic precipitator, and the backhouse filters to remove them. And in terms of the efficiencies, the cyclones have moderate efficiency, generally, I would say below or around 50 to 60%, right? The ESP is somewhere around 97 to 99%, while the backhouse filters will almost have 100% efficiency, right? Mainly because they're operated with different mechanisms. So we also talked about the sulfur dioxide and nitrogen dioxide, or I should say nitrogen oxides, right? So before we talk about how we control them, we first introduce how to do the unit conversion, because there are a lot of scenarios where people have to convert ppm or ppb into, let's say, microgram per meter cube or nanogram per meter cube, right? So we show that we can do these unit conversions by using the ideal gas law. So basically, we can convert everything from one type of unit to the other type of unit. So further, we introduced how we can remove these air pollutants. Basically, for the sulfur dioxide, people created a device called the limestone scrubbing, which is introducing the flue gas into a tank reactor. right? This is the inlet, and here the outlet is at the top, right? And within this tank reactor, here we just create sprays of colloids. We're generating droplets that's falling down, right? In terms of the colloids, it contains calcium carbonate, which is basically the grinded limestone with water, right? So they're going to react with the sulfur dioxide and then further get into solids. Let's say the calcium sulfate, right? We get calcium sulfate by further introducing oxygen to oxidize this sulfur dioxide into sulfur trioxide, right? And then we can collect the solid at the bottom, mainly because the calcium sulfate has a very low solubility, right? So this is the way we control the sulfur dioxide. And in terms of the nitrogen dioxide, people just mainly make modifications to the combustion because people found out that basically with a higher temperature and with the higher residence time of the pollutants in the combustion or in the combustor, the more the nitrogen oxides, right? And because of that, we created a technique called the overfire air, which is burning these fuel, these coal particles into different stages, right? We have the stage, let's say at the bottom, which is burning most of the fuel, but with a very low oxygen, right? So in this way, we can reduce the temperature of the combustion. And at the same time, over this fire, we have the air that's just composed of oxygen and nitrogen, right? So in this way, we can basically react with the remaining organics. So the flow is going upwards within the combustor, right? So we're separating the combustion of the fuel into multiple stages. At the same time, we reduce the time of the pollutants. At the same time, we reduce the oxygen within this combustion here, right? So in this way, we can control the nitrogen dioxide emission. So there are also control methods using the catalytic reactions. For example, in the nitrogen dioxide control, we have the SCR, the selective catalytic reactions, which is going to react these nitrogen oxides back into the nitrogen. Okay, so these are the control methods for these particulate matter, sulfur dioxide, and nitrogen dioxide. So as I mentioned earlier in the class, not only these pollution control are important, but also the meteorology or the transport of these air pollutants are important, right? As for example, the case that I give, if the most of the air pollutants are just blowing over the ocean, then we don't need to care about that too much, because those pollutants are going to settle down or going to react within the atmosphere over the ocean, where basically very few people live on the ocean, right? So the health impact will be much lower. So that's why we have to understand this pollution transport. And we know that these pollution transport in the air is mainly caused by wind, right? So if we talk about wind or the reason for generating these wind, of course, it's because of the pressure difference, right? So basically the wind is blowing from a high pressure region to the low pressure region, right? So just imagine when you exhale the air from your lung, right? Say if you blow the air, right? So it's the high pressure in your mouth that's blowing the air into the ambient environment, right? And further, I would say our Earth is actually the reason why we create this pressure difference is a temperature difference. So the region where we have these high pressure regions normally have very low temperature, right? So low temperature region will correspond to a high pressure, and then the high temperature region will correspond to a low pressure, right? So basically, it's the difference in the temperature, I would say delta T, that's creating this this direction of the wind, right? So because of that, we have this regional wind patterns and also the global wind patterns, and we're going to talk about that later. So further, we're going to introduce the atmospheric dispersion. So not only the wind is important, but also the dispersion or the diffusion of the pollutants is quite important, right? For example, if we have a stack and we know that the wind is blowing in this direction, right? We know that then the pollutants are going to go in this direction. But at the same time, the concentrated pollutants are going to basically disperse at all directions, right? From left to the right, right? And also up and down, right? So generally we can use the equation or the Gaussian model to simulate this dispersion of the atmospheric pollutants. And that will involve, or that will lead to the stack design where we can better control the transport of these pollutants, or also to evaluate, let's say, if we know that there's a stack a kilometer upwind of our location. So how can we evaluate, or how can we simulate, calculate what is the concentration of the pollutants without just doing directly the measurement, okay? So first we'll talk about the wind. So as I introduced earlier, the reason why we have wind is because of the temperature difference. So normally the higher temperature region have a lower pressure, right? And the low temperature region has a higher pressure. So this is actually the reason why we can see these, what we call land breeze or the lake breeze, or if it's nearby the sea, people also call them ocean breeze, right? So here I'm giving two examples. One is during nighttime, one is during the daytime. So let's say for the daytime, then we know that the solar radiation is going to warm up the land, right? So basically over the land, it's going to have a warmer temperature. The temperature is going to be higher. And then over the ocean, the temperature is lower, mainly because the water has a very high heat capacity, right? So it can absorb more heat while the temperature is not rising up. So because of this temperature difference, then we know that the pressure here is going to be lower and pressure here is going to be higher, right? So then we're going to have this recirculation. So the warmer temperature, the air is going to rise up, right? Lower temperature, the air is going to settle down. And at the same time, the higher pressure region is going to blow the wind towards the low pressure region. And then because of that, to make this mass balance here, at the top of the atmosphere, the wind is going to blow in this region. So basically, we're forming this recirculation of air during the daytime, right? This is what happens over the lake or what happens over the ocean. So due to the similar mechanism at night, we're going to have a colder temperature over the land and then the warmer temperature over the water or over the lake, right? Temperatures rise up, temperature cool down, and then the pressure over the water is going to be lower and the pressure over the land is going to be higher. So we're going to form this backward type of recycle or the circulation of the air. So this is the reason why we have these land breeze or lake breeze, right? So now if you consider, let's say, instead of a lighthouse, we have a stacking here, right? We also have some populations over here. Then we can basically try to predict what is going to be the air pollution situation here for people living in this region, right? So during the daytime, then it's going to be controlled by the lake breeze or the ocean breeze, right? So the cleaner air is going to be blowing towards these population here, these people here. So the air is going to be cleaner. But at nighttime, since the wind pattern is reversed, then these pollutants are going to have a higher chance of floating over these area where people live. So it's going to lead to a basically a worse air quality, right? So here I'm also giving a satellite image, which is showing the basically the cloud situation over some islands. right? So definitely this is showing the daytime because we can still see these islands here, right? You see that there are a lot of clouds over these islands, and people also call this as the island effect. So this is also because of the ocean breeze. Basically, you have a warmer air over the land, right? So the air, this is during daytime, right? So the air is going to blow in this direction here. And then at the same time, we should know that the air that's blowing over or from the ocean are going to have a higher relative humidity, right? It's saturated with water. So when the air is rising up, the temperature is going to get cooler, and then we're going to form more clouds. So that's why, because of this land ocean breeze, right, we're going to form a lot of clouds over the islands. And this is also called the island effect, right? So this is about the regional wind. And I think another example can be the mountain valley breeze. Yeah, I think I wrote it out here. So in terms of the mountain valley breeze, it's similar to these land lake breeze. Basically, you have tall mountains, and during the daytime, the top of the mountain is going to be warmer because it's closer to the sun, right? It's receiving more solar radiation. So the temperature is going to be warmer, and then you're going to have air rise up, right? And in terms of the valley, temperature is cooler, right? The air is falling down. So because of that, you have a circulation pattern like this, right? And at night, this the direction of this circulation is going to be reversed, right? So this is, I would say, simple examples showing how the wind pattern in regional area is affected by temperature and also affected by pressure. So the same mechanism can actually work on our Earth, right? So here, I think I have a video, and then maybe I can also show that from the. Just a second. All right. So here, what I'm showing is the global wind pattern. This is actually the transport of aerosols on our Earth. So if you just look, let's say, in details about, I mean, try to understand what are the general patterns. So if you just look at the equator region, right? If I ask you what is the general wind pattern near the equator region, so you can see that actually most of these aerosols or these pollutants are flowing from east to the west, right? Although there are some swirls, but in general, they're flowing from east to the west. And what's showing here is basically the Sahara desert, right? It's transporting a lot of dust to the North America and also to the Amazon forest, right? So this is over the equator region. But if you go to the mid-latitude, you see that the wind direction is reversed, right? So in the mid-latitude, the wind is blowing from west to the east, right? And the same, actually, same direction in the southern hemisphere, from west to the east. And then if you further go up to higher latitudes, you can see that the wind direction is reversed again. So you see that the mid-latitude from west to the east, while in the higher latitude, it's actually from east to the west. Okay, so the wind direction is reversed again. So at the same time, you can see that there are a lot of swirls. So I think people also call them hurricanes or tornadoes. But if you just look at what is the direction of this swirling movement or the rotational movement. So you see that in the northern hemisphere for these swirls, maybe I can just pause it for some time. Let's see if we can, yep, here. So you see that for this tornado here, in terms of its direction, it's flowing counterclockwise, right? But if you just look at what's happening in the southern hemisphere, it's flowing clockwise, if you see here, right? It's a clockwise rotation. So what is causing these general wind patterns? What is causing these features, right? It is actually still because of the wind that's happening in the, let me just share my screen again. So it is still because of the temperature difference, right? Still because of the pressure difference. So I can try to explain what is happening regarding the wind direction from east to the west or from west to the east. So basically here, what is showing is the solar radiation that's reaching to our Earth. So because our sun is so large, right, compared to the diameter of the Earth, we can treat those solar radiation as parallel, right, the parallel lights, right? And then if we just look at the cross-sectional view, let's say just this view here, right? So the amount of solar radiation in this band, and in this band, they're the same because they have the same width, right? They have the same solar radiation, or I should say the same heat within this solar radiation, right? But if you just further look at what area the solar radiation is shining upon, right? For the equator region, it's directly shined upon a very narrow area of the Earth, right? But in the mid-latitude, the area is longer, the area is larger, right? And for the higher latitude, it's further larger. So basically, for the same amount of solar radiation, it's being shared at a larger area at higher latitudes, right? And because of that, we know that the temperature here is going to be cooler. So this makes sense, right? Whenever we talk about the North Pole or the South Pole, the temperature is cooler, while at the equator region, the temperature is higher, right? So if you just think back on the movement of the wind, right? The lower the temperature, the higher the pressure. The higher the temperature, the lower the pressure, right? So theoretically, if our Earth is just a billiard ball, if our Earth is a very simple geometry, a very small sphere, then what we would see is that the wind is going to flow from the high latitude to the low latitude or to the equator region and rise up over the equator and then go back to the polar region, right? It's going to follow this type of pattern, right? But unfortunately, our Earth is not a very simple sphere. Our Earth is so large, it has a very large diameter, so it cannot sustain this long range movement of the air, or of the wind. So what happens is that actually this wind pattern is broken into 3 different cells. Okay, so in each cell, it still satisfies this wind direction blowing from the higher temperature, from the lower temperature to the higher temperature, and then basically create these wind in the regional or the sub-global type of scale, right? So this is what really is happening on our Earth, right? So you see that in the equator region, what we call is the Hadley cells. So in the Hadley cell, as we said, the temperature here is higher, right? The air is going to rise up, right? The temperature here is lower, so the air is settling down, and we have this type of recirculation. So in the polar region, you see that the North Pole is going to have a cooler temperature, right? The temperature is cooler, so it's going to blow the wind in this direction, right, to the mid-latitude, and then since the mid-latitude has higher temperature, it's going to rise up and then blow back. Okay, so this is what happens in the equator region and in the polar region. But in the mid-latitude, you see that since we have these 2 cells, that's basically forcing the air to settle down in the mid-latitude and to rise up in the higher latitude. So the cell that's in the center is going to basically be forced by these 2 cells, cell 1 and cell 2. So the air is going to settle down in here and then rise up in here. Okay. So this is going to be the new wind patterns on our Earth. So instead of being a very long range of the wind sweeping from the North Pole to the equator, right? We're going to have these three different cells, okay? So this is going to be the wind pattern, let's say, in terms of the height, right? In terms of at different heights, you're going to have these different directions of the wind. But further, there are directions from west to east and east to west. So you see that if we just look at the surface wind at the equator region, right? The surface wind is going to blow from north to south, right? But you see that they also bend to the right on our Earth, right? And instead of directly blowing perpendicularly towards the equator, they actually bend to the right. So there is a direction, or west to east or east to west direction in these global wind patterns. And the reason for that is the Coriolis force. So I think maybe in geology or in high school, you probably have heard of this force before. So basically what happens is, if you just imagine we're trying to throw a dart from the North Pole to the equator region, right? So our Earth is always rotating, right? So basically at each location on the Earth, there's going to be a linear velocity that's rotating around this axis, right? So, but since we're having the same angular velocity, the linear velocity or the line velocity at different locations is going to be different, right? At the equator region, it's going to have the largest line velocity, while at the North Pole, it's going to have the lowest velocity. So now if we just throw this dart out, right? If we're trying to point the city in Chile, right, Quito, then since this dart doesn't have any linear velocity, it's going to have a very low linear velocity, right? So, and the Earth is also rotating, right? So the dart is going to have a velocity difference compared to the ground, right? So that's why the dart is going to lag or travel slower compared to the Earth, and then gradually bend to the right. Okay, so this is because basically the dart that we throw out doesn't have any linear velocity. That's basically rotating with the Earth, right? And there's a velocity difference, and that's why it's bending to the right. Okay, so this is what happens over the northern hemisphere. So the same thing will happen, let's say, if you just throw the dart towards the North Pole, right? Let's say we're trying to throw this dart in this direction. So since at the equator region, we have the largest linear velocity that's going or moving with the Earth, right? While the land at mid-latitude or at North Pole doesn't have that high velocity there. So the dart is going to bend to the right, okay? Mainly because it has a larger velocity in this direction here. So that's why, or this direction here, this actual force here is called the Coriolis force. On the northern hemisphere, it's going to bend this movement towards the right. And in the southern hemisphere, it's going to bend this movement towards the left. So I think an easier way to memorize these directions is that this is what I heard from another professor. So basically, since we're living on the northern hemisphere, right? So we're always right, okay? So it doesn't mean that people living on the southern hemisphere are wrong. It means that they're left, okay? They're going to bend to the left. So I hopefully this will make it easier for you to memorize the direction of the Coriolis force. So also because of the Coriolis force, so maybe now we can explain why the wind direction is blowing towards certain directions, right? So basically in the equator region, we know that the wind is blowing from north to the south, right? And because of the Coriolis force, it's going to bend to the right, right? So that's going to create this movement of the wind from east to the west, okay, at the equator region. So remember that dust from the Saharan desert, right? So dust is blowing from the Africa towards North America and the South America. And then in the mid-latitude, also because of this Coriolis force, it's going to blow the wind towards the right, right? It's going to blow from west to the east. So the same thing will happen for the North Pole. The wind is going to bend to the right, okay? So now if I ask you, if we want to build a new power plant in the US, remember it's in the mid-latitude, right? We're in here, okay? So where should we build it to minimize the impact of the air pollution? So this is a quiz question, and you can choose the answer for that. So I'm going to show this wind pattern again. Okay, 5 more seconds. Okay, we'll stop here. All right, so I think most of you are correct. We should build them in the or near the East Coast, right? So this is just to consider to minimize the impact of the air pollution. So it's not about how easy or what is the cost for transporting the electricity here. Of course, building in the East Coast will be easier for us to transport the electricity, right? But in terms of the dispersion of the air pollutants, building it near the East Coast is going to be better because most of the pollutants are just going to be blown over the ocean, right? Where no people are living on there. So we don't need to worry too much about the air pollutants, okay? So this is the Coriolis force and how it affects the global wind pattern. So the Coriolis force is also the reason for the clockwise and counterclockwise movement of these cyclones or these tornadoes, right? So we know that the tornado happens when you have a very low pressure at the center, right? And then you have a high pressure surrounding it. So that's why the wind is going to blow from all directions towards the center, right? And the reason why we see clouds, basically, if we just see from the side view, let's say we have the air that's rising up from the center and the wind is blowing from the surrounding locations toward the center, right? So the cyclones over the ocean actually, for these wind here, it's saturated with water. So and they have very high relative humidity. So when the air rises up, the temperature cools down, right? We're going to form a lot of clouds over, basically over this low pressure center. So that's why we have these cyclones really has something like a white cap over it, right? So the reason why we have these counterclockwise or clockwise directions is also because of the Coriolis force. Because if you consider, if we're living on the northern hemisphere, then the wind is going to be blown towards the right. Okay, since we're always right. Okay, so if it's blowing towards the right, then you can see that it's going to be a counterclockwise direction. Well, in the southern hemisphere, if it's still having the same high pressure to low pressure directions, now we're going to bend towards left. Okay, so that's going to give it a clockwise direction. All right, so it's also because of the Coriolis force. So now we can use the rest of the time to talk about the atmospheric dispersion here. So the atmospheric dispersion is closely related to the temperature variation that's as a function of altitude, or as a function of height. So in general, let's say if you climb up a mountain, you can feel that the temperature is going to get cooler as you climb up. right? So this decrease of the temperature can be calculated with the dry adiabatic lapse rate. So in general, if you climb up 100 meters, then the temperature is going to decrease by around 1 Celsius. Okay, so people have been measuring the temperature as a function of altitude. So here is showing basically the altitude in the y-axis, and here in this graph, it's showing the temperature in Kelvin. Okay, so you see that in the troposphere, the temperature is always cooling down, always decreasing, right? Until an altitude of around 15 kilometers. Okay, so the temperature is always cooling down here. And then we know that above the troposphere, we have this layer called the stratosphere, where the ozone is being depleted, right? So you see that in the stratosphere, the temperature rise up. This is mainly because of the ozone layer here, which is converting the UV radiation into heat. Okay, so just think back on the ozone depletion where we have the chemical reactions, right? So basically, and further higher up, since we don't have any ozone further higher up, it's called the Mesosphere, which is further higher up, right? Up to around 80 kilometers, right? I don't think anyone is living at that altitude, right? So basically, this is the general temperature profile as a function of altitude. But in terms of the atmospheric dispersion, under a lot of situations, the temperature profile doesn't look like this. Okay, so this is the normal, I would say, the theoretical temperature variation. But there are a lot of scenarios that may cause the perturbations. For example, the surface temperature of the Earth, let's say the temperature at the ground, can have a lot of fluctuations. For example, it can be lower due to cooling. For example, during nighttime, where we just shut off the solar radiation, the temperature at the ground is going to be cooler, right? So if the temperature is getting colder, the pressure is going to get higher. So the air is not going to be able to rise up anymore, right? For example, if we have a stack that's emitting pollutants at night, right? If it's during the nighttime, then the air, because of the cooler temperature and the higher pressure, the air is not going to rise up. So what that means is that the pollutant that's emitted by these by this stack is just going to get trapped in the layer or trapped near the ground, right? So it's very difficult for us to disperse these air pollutants. But during the daytime, let's say during noontime, because our Earth is fully heated, right? So the temperature is going to rise up and the pressure gets cooler, right? So that's going to be easier for these pollutants to disperse. Basically, they can get dispersed to larger areas, right? So because of that, the concentration will get lower because they're dispersing, right? So that's going to be a better condition for the emission of the pollutants, because in this case, since it's being transported to a larger area, then the health impact will become lower, mainly because the concentration is much lower compared to the nighttime situation, right? So we call this surface cooling condition as the stable condition, because the atmosphere is very stable. There's no movement. Well, for this heating condition, we call it unstable condition. Okay, so here basically it's showing the conditions where you have stable and unstable air. So for example, the dry adiabatic condition is the theoretical condition of the temperature decrease, right? It's around 1 Celsius per 100 meters. Well, the dry adiabatic lapse rate is shown in the dashed line here, okay? While the surface temperature can be different, right? If the surface temperature is higher, right, this is unstable condition. If the surface temperature is cooler, this is stable condition. So this is going to lead to completely different conditions in terms of the air pollutant transport. For example, here in this image is showing the weather condition, let's say over the Bay Area, okay? So you see that it seems that there's a very thin layer of air where all the pollutants are trapped nearby the ground. Actually, this is because of the cooling of the surface overnight. So this is early morning, right? Where the pollutants have not been dispersed into the larger area yet. So because of the higher concentration of the pollutants, then the health effect is going to be stronger. So here is another image showing the transport of these pollutants from stacks. Okay, so this is at nighttime, right? You see that these pollutants are not going to get dispersed higher up. It seems that they're trapped by the atmosphere, right? At a very low layer of air. So because of that, let's say if people ask us if a higher stack height can help solve this problem, we should say yes, right? Because if we can build a stack that can penetrate through this stable layer of air, then basically we can get these pollutants emitted or dispersed very quickly, right? So it doesn't get trapped into the atmosphere and lead to healthy effects, right? So because of these air stability issues, people have been trying to predict what is the transport pattern of these pollutants coming out of the stack. Okay, so there are standardized equations to calculate the air pollutant concentration that's downstream of a stack. So here is showing a schematic diagram of a stack emitting pollutants, right? You see, basically what we can calculate is any location at the ground. Let's say it has a location of X, Y, and in terms of the height is 0. Okay, so the X is basically downwind of this stack, and Y is perpendicular to the wind direction, right? We can calculate what is the concentration of air pollutants at any location downwind of a stack. So we can use this equation here to plug in the values and then calculate that. So if you further look at these different terms, okay, so for example, for this term, and for this term here, so they look very similar to the Gaussian distribution. So the Gaussian distribution, basically, it has the highest value at the center and the lowest value when it's away from the center, right? It is quite understandable for the dispersion of the air pollutants. For example, if you're talking about the concentration within this plume of pollutants here, so it's going to have the highest concentration along the center line, right, near the center of the plume. So this is talking about the concentration that's along the X direction. I should draw it here. Along the Y direction. So the concentration is going to be the highest at the center line, right? And the concentration is going to be lower when you're away from the center line. So the same will happen along the Z direction, right? So basically, again, the concentration is going to be the highest at the center and lowest when it's away from the center. So that's why this model is also called the Gaussian model to predict the dispersion of the air pollutants. So there are some parameters we should use to do this calculation. So you see that this equation here will tell you what is concentration of air pollutant at any XY location. If you know the height of a stack or the effective height of a stack, okay? So it's calculated with a few parameters. For example, the E here, this is the emission rate of the pollutant. So people can just characterize at the, let's say the power plant and know what is the emission rate. So it's also determined by SY and SZ. So the SY and SZ are basically the standard deviation, or it tells how dispersed these pollutants are. For example, if it has a shape like this, right? Then it has a small sigma or a small sigma Z, right? It's quite concentrated. But if it has a dispersion that looks like this, then it has a higher sigma Z, right? It describes how dispersed these air pollutants are. And then U here is the wind velocity nearby the stack. And then since we're plugging in Y here, we can just plug in this value here. So the H is called the effective stack height, right? So it's not only the stack height, because we know that the air pollutants are still going to rise up a little bit because the air is not stagnant at the top of the stack, because there's velocity of the pollutants rising up, right? So we need to basically calculate this effective stack height as H, which is the actual stack height, plus delta H, right? So this delta H, or I should say capitalized delta H, is further calculated with this equation here, where you have the, when you need to plug in what is the velocity of the air in the stack diameter, the wind velocity, right, and temperature of the stack plume, right, and so on. So basically, if you know, if you can calculate these parameters, you know that we have emission rate, we have velocity of the air, we have, we don't have sigma here, we have H, Y is ready. So the only unknowns are the S, or the sigma Y and sigma Z, or the SY and SZ. Basically, that's the parameter that's determining how spread or how dispersed these air pollutants are. So we can further determine it with this table here. So we can categorize our atmospheric stability into different types. So we can have the very unstable condition, very unstable, or the very stable condition. So under the very stable condition, we're going to have smaller SY, right? Basically, it's more concentrated at the center. And of course, it's also dependent on how, what is the distance downward, right? You can imagine that when it's close by the stack, it's going to be more concentrated or more narrow, right? When it's further downwind, it's going to be more spread, okay? So there are also equations where we can do this calculation to find out what is SY and SZ. I would say that maybe we can also quickly go over this, next class, but you do have a few homework problems on this type of question. So I would suggest that maybe you can go over this example problem first, and then we can talk about this question, next class. So again, our next class will be a face-to-face class. All right, I'll send you more notifications if we will have any nearby that time. All right, so that's all for this class. Let me know if you have any questions.